Hello and welcome to Answer Everywhere. Today we are taking a look at QEMU, the emulator. I don't even know. I don't know. Maybe I'm supposed to pronounce it Camus, like Camus, the philosopher. I don't know. I was curious. People were talking about the developer Fabrice Bellard, who apparently also wrote TinyCC, which we've taken a look at before on the show. And that made me curious when QEMU came out. Here's the stable release. Where is the initial release? We have a tiny code generator. Aims to remove the shortcoming of relying on a particular version of GCC or any compiler, instead incorporating the compiler code generator into other tasks performed by QEMU at runtime. So is this related to the TinyC compiler? I'm not sure. And we don't have anything on the history. QEMU. Okay. Originally developed, according to this wiki, the Game Tech Wiki, originally from 2003. It emulates a wide range of architectures beyond x86 and has been used in Android emulation, both officially and unofficially. It's well known in the server industry for its handling of virtual machines using KVM and, more recently, libvirt. Okay. So let's take a look. They have an official mirror here. And in fact, I'm not really sure that I understand the distinction between... So this should be an emulator. But I know that it handles... it uses KVM, which I thought was a hypervisor. So aren't hypervisors and emulators distinct? I would think that the hypervisor uses since typically it's the same arch that it uses essentially the bytecode gets passed through, whereas emulators like emulate the CPU instructions. Virtual machines make use of CPU self-virtualization to whatever extent it exists to provide a virtualized interface to the real hardware. Emulators emulate hardware without relying on the CPU to be able to run code directly. Okay, so Box is an emulator. We've looked at Box. QEMU is also an emulator, although with the use of kernel-side KQEMU package, it gained some limited virtualization capability when the emulated machine matched the physical hardware. But it could not really take advantage of full x86 self-virtualization. KVM is a virtual machine hypervisor. So does that mean that if you run... I want to dig into this further. So can QEMU run fully virtualized KVM VMs? Where am I from? I'm from the USA. I'm in the New York region, the New York area. All right, KVM versus yeah, all right. Okay. So I thought that they could be used together somehow, but maybe I'm misunderstanding. All right, back to the code. All right, this is huge, a huge project, and we're not going to get to all of it. And not only do we have many directories, we have many C files outside of those directories. And so we're going to have some sort of plan for what we want to see. I see some Linux headers here, Linux users, some migration stuff and monitor stuff. FS dev I'm gonna guess is like file system development. FPU, maybe floating point unit. eBPF, it should be eBPF. We've looked at eBPF in the Linux kernel on the show before. You can find that video. I'll link it in the description. Dump, I'm not sure what dump will be. Maybe that's like dumping information about the emulated machine. Crypto, contrib, configs. Common user, cardev. Character device, I guess, rather than character development. BSD user, I'm going to guess this is just like we had Linux support. This is just BSD support. Block, I assume will be like block device stuff. Authorization, audio acceleration and acceleration. In PC BIOS, Python, QAPI and QGA, I don't know what those will be. QObject, maybe that's a QEMU object. And who knows what COM is. All right, so how are we going to want to do this? I think I want to go back to Emacs. Because that way I can at least click around. I don't know. I'm feeling a little bit intimidated. So let's jump in and we'll make some mistakes along the way. One thing we can open up is whatever looks kind of main-y. Do we have a main.c? I don't think we do. Do we have an int main? We have system main. We have BSD user main. I'm going to guess system main is the place we want to be. So we'll open that up. What else do we have? IO, is that interesting? I don't know. Let's open up things that I'm not sure what they are as well and that have queues in them. Those might be interesting. ROMs should be read-only memory of some sort. We have some commands, HMP command info. I don't know what that is. Job, I'm going to guess is maybe some sort of background job. This is build system stuff. Page, very common. And bridge helper. QEMU image. Whatever SASL is. Key map options. We actually don't have a whole lot of C files. I guess we'll look at block device, block job, and block. And we'll just pick a few folders like system, target. I'm going to guess that maybe target is like the target architecture. So this might be the directory that says, if you want to pretend that you're running on whatever Sun Spark 64, that'll be the folder that has the emulations for those things. And then a lot of this is really going to be like piping and modeling of things like hardware that you have to support. We'll open hardware, we'll open IO. I guess we'll open up FPU. Oh, actually backends, maybe what I was thinking targets was. So let's open backends here. So backends has confidential guest support. I don't know. I'm curious enough about this. Let's open this in a new window. From Red Hat. Let's just find out what this is. QEMU, confidential guest support. Is it like the emulator doesn't know anything about the thing you're emulating? Traditionally, hypervisors such as QEMU have complete access to a guest's memory in other state, meaning that a compromised hypervisor can compromise any of its guests. A number of platforms have added mechanisms in hardware and or firmware, which give guests at least some protection from a compromised hypervisor. Okay, so this is some support for, so AMD SEV is an example. Okay, so that's support for something closer to like trusted computing, so you can maybe like run things on a cloud environment without having to trust the cloud provider. At any rate, in the backends, the other things we have are CryptoDev vhost user, CryptoDev, dbus VM state, host mem, IOM muffed random number generator, trace events traced, and some other stuff. And whatever TPM, maybe trusted platform module. TPM configuration. I'm going to guess that this is all kind of related somehow. TPM backend init. I don't know what any of that stuff is doing. Okay. So backends maybe doesn't look fundamental, but we might return to it. So here's QEMU system main. Main is really simple. We're just going to call QEMU init and then return QEMU main of nothing. And QEMU main is QEMU default main, which is going to call the main loop and then clean up when the main loop exits. And the main loop is presumably going to run forever until you're finished with your thing that you're emulating. Do we get to see the implementation here? No. Can we go to systemu.c? Also no. What is sysmu? And is this all header files? Okay, whatever. So we have this main loop thing. What else do we have? We have cleanup, restore boot order, validate boot devices. I'm going to guess that's mainly just like sanity checking and maybe permission checking. You can have you get the device list, add boot device path, etc. And we have, just looking at some of the types, we have device state, which I'm going to guess is a relatively general type for all sorts of devices that we can emulate. We have object, which is an extremely general type, and some other stuff. And then what do we have? Some external stuff like legacy drive options, runtime options, character device options, etc. Okay, I have no idea what NBD is. Something, maybe some debugger. We have client connection, client, common, NBD internal server, and some trace events. Let's look up NBD QEMU. Network block device server. Okay, so some sort of network block device. Bind a dev NBDX block device to a QEMU server on Linux. I don't know. Does that include, is this like a specific protocol? Or is this like on Linux, a network block device is a network protocol that can be used to forward a block device, typically a hard disk or partition, from one machine to a second machine. As an example, a local machine can access a hard disk that is attached to another computer. Alternative protocols are iSCSI, NVM, loop device, DRBD, etc. Okay. I guess that's like maybe at a lower level than NFS. The block device is by definition a device that stores or reads data in blocks. This means there's always a certain amount of data is transmitted at every operation. A file system is how your disk is formatted. It manages how the data is physically laid out. Okay. So why are they called file systems then? Blah, 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 blah. NBD is good for what? Besides just being an online storage, diskless workstations. One can boot the computer with PXE into a small live Linux from where the NBD can be mounted on an operating system booted. There's no local disk. All data is central. Okay, this is maybe for like super thin clients. All right, so this is network block device support. We don't really need to look at that. Here's QPA. I don't know what QPA is. Maybe main will tell us. We have dev vtcon. I said QPA, but I meant QGA. Global guest agent. GA might be guest agent. Let's find out. QPA, QEMU. Oh, sorry, QGA. I keep doing that. Yeah, okay, guest agent. The guest agent is a daemon intended to run within virtual machines. It allows the hypervisor host to perform various operations in the guest, such as get information, set the guest system time, read write a file, sync and freeze the file system, suspend the guest, reconfigure the guest's local password, and set the user's passwords. Okay, so this is guest agent support, I believe. And what can we do? We have quit handler. If we're frozen, don't exit unless we're absolutely forced to, because it's basically impossible for graceful exit to complete unless all log PID files are on unfreezable file systems. There's a very likely chance that killing the agent before unfreezing the file system is a mistake. Okay, so we check if it's frozen, and if it's not, then wait, we want it to be frozen, right? If we are frozen, don't exit unless we are forced to. Killing the agent before unfreezing the file system is a mistake. Okay, so there's some, we want to check whether we're frozen, and there's badness that happens if we get that wrong. We can register some signal handlers. We get a G boolean back. What is G? Is this like GTK? Or is it just glibc? Yeah, it's just glib. Okay. Fine. Okay, so when we register signal handlers, we get a boolean back. We pass nothing in. So where do we get the signal handlers? I don't know. I guess they're hard-coded. So sigint and some sigact. I don't know where sigact came from. I guess that's the thing we're registering. And whatever, and null, I guess, maybe says do nothing. And then we're registering sig term. And we set the sigact handler to sig ign and check some sig pipe stuff and return true. All right, what else can we do? Reopen fd to null. So I guess fd must be file descriptor. Use this in place of all post fork fclose callers. So you pass it in a file descriptor, and then we set null fd to be opening of dev null. And if null fd is less than 0, we return. I guess that means there's an error. Otherwise, we call dupe2, setting fd, I think, to null fd. And if null fd is not, so if after doing that, they're not the same, then we close null fd. Okay, I'm not sure why we do that, but it's like nullifying some file descriptor. We have this usage thing where you pass in a command. Oh, this is just some, is this just like printing out the usage statement? Yeah, this is just some like usage statement. Okay. All right. So that's some guest agent stuff. Let's see if there's any other guest agent stuff that we want to look at. We have some commands. Let's look at the commands Linux. We have things like build file system mount list from mtab. So we're going to look at mtab and build some mount list, I guess, and return it where. We're going to say whether it's true or false, whether we succeeded or not, and then we might have some error. And where does it get put to? I'm not sure. I guess mounts must be an out thing because we're reading from mtab, right? Okay. So that's one thing we can do. We can decode mount name. And what else? Guest fs freeze do freeze list. Walk a list of mounted file systems in the guest and freeze the ones which are real local file systems. Okay, so that must do exactly what it says. We're just going to have some list. And if it's a real file system, then we're going to freeze it. All right, and then you can thaw them. So these are just some of the things that the guest can do. We're going to just move along. Greetings from Iraq. Hello. The Iraq of Europe. Serbia. Hello. Welcome. How are things in... So that means you're in Serbia, right? How are things in Serbia? All right, so here's QAPI, which I'm going to guess is just the QEMU API. And we have a bunch of stuff, including some JSON stuff like ACPI.json, machine target.json, and then a bunch of C files. Let's look at ACPI.json. ACPI table operations. Specify an ACPI table on the command line to load. At most, one of file and data can be specified. The list of files specified by one of them is loaded and concatenated in order. So we have some ACPI table options. This is just some JSON that I guess is representing a struct. And then presumably you read this in and populate the C struct based on the information, hopefully with some cleaning somewhere. So for example, the OEM ID, maybe original equipment manufacturer, you set it as some string, and so on and so forth. How about audio.json? Audio dev per direction options. We have some mixing engine, or rather we can turn on and off the mixing engine, whatever fixed settings are, and some frequency, channels, voices, format. And then here's ALSA stuff for the ALSA system. Some core audio stuff. Do we have Pulse? We have Jack. So for Jack, we have the server name, client name, connection ports, whether to start the server, and exact name. Use the exact name requested, otherwise Jack automatically generates a unique one. Okay. Terrible. Oh, I'm sorry to hear that. All right, so that's the those JSON files are how you load data into the I guess into the API. I don't know if that's user visible or if that's just used by the QEMU project to save state or something along those lines. And what else? So we have an event, QMP event. Let's look at QMP event, QMP dispatch, and then we'll move along. We're going really quickly through this one because it's so huge, and I don't know yet where the really interesting stuff is. So you have QMP event build dictionary. You give it some event name, which is just a car. It doesn't seem to have an event type yet. Build a QDict, and then fill the event name and timestamp. Caller should feed the QDict after use. So I don't know. This is just building some dictionary of events. An event is just really a string with a timestamp. I don't know what MP is. We could try QMP, QEMU. QEMU machine protocol, presumably. The QEMU machine protocol is a JSON-based protocol which allows applications to control a QEMU instance. Okay, so I guess this is just some application can control some QEMU instance. All right. And some QMP dispatch. Let's ask about, tell me about your favorite uses of the QMP protocol from QEMU, and pretend we'll just take one of its suggestions, like your Mowgli from the Jungle Book, before answering. Let's pick another character. That seems like that's likely to lead to some insensitive representations, and I'm not sure why they're suggesting this. But how about pretend like you're Optimus Prime when you reply. And while it's doing that, we're going to move along. So QObject, I'm going to guess, is mainly their core types, and that seems to be consistent with what I'm seeing. But for example, I see QBool, QDictionary, QJSON. So these are just going to be types that are probably optimized implementations, or at the very least, they have like extra fields that are that they want to use for all of them. So let's just choose, how about QString? We are in, I think, just regular C, maybe? So QString, we have the string new thing, string from substring, et cetera, and we can unref a string. So I guess, is it a QObject under the hood? So we're doing maybe some object counting. QObject init. Is QObject just all about counting, reference counting, I mean? We get no real comments. Do we have a header, QObject.h? We have com_QObject.h. Based on ideas by Avi Kivity, or Kivity. QObject reference counts terminology. So returning references, a function that returns an object may return it as either a weak or a strong reference. If the reference is strong, you're responsible for calling QObject unref on the reference when you're done. Okay, so this is the caller's the callee's responsibility. If the reference is weak, the owner of the reference may free it at any time in the future. Before storing the reference anywhere, you should call QObjectRef to make the reference strong. Transferring ownership. When you transfer ownership of a reference by calling a function, you are no longer responsible for calling QObjectUnref when the reference is no longer needed. Okay, so this is all ownership stuff that would be if you have like modern C++, I think you can just use like standard weak ref, standard move, all of that unique pointer, all of that stuff to handle ownership semantics. And then if you use Rust, I assume that the borrow checker is taking care of all of that for you. But where we are, which I think is in C, I think GitHub will tell us. C, there's a little bit of C++. So you have to do your own implementation, I guess. And we're not going to really dig into it. I think that comment was enough to tell us what was going on. And let's see what Energon reserves online. Okay, so precise QMP lets you control a QEMU instance with pinpoint accuracy, flexibility on the battlefield. You can send real I want real applications of when you would want to add QMP support to your application. Okay, here's QOM. OM is, I don't know. We see more object stuff. Object model? I don't know. We have struct type impl. so type implementation, we have a name, a class size, instance align, class init, class data, object class. So this looks like this is just some implementation of a class system. Type new, called on type info, will malloc a type impl thingy struct, do some asserting that the name isn't null, and then we'll look up stuff in the type table. So is this where did we see? We saw the tiny object something or other on Wikipedia. So let's look at QEMU again. Tiny code generator. I wonder if this is part of the same stuff. The QEMU object model, so I guess that is what QOM is, provides a framework for registering user-creatable types, and instantiating objects from those types. It has the following features: system for dynamically registering types, support for single inheritance of types, and multiple inheritance of stateless types. Okay. So we are implementing some type system. I don't know. It says it's for users. I'm not sure if the users are I'm not sure who the users are. Are the users like people who implement additional functionality on QEMU, or is it people who are running virtual machines in general? User creatable types. They just stole this language for Wikipedia. I mean, it seems like Wikipedia just copied this, is what I'm saying. I don't know if that's legal. What's the license here? In the manual, or okay, sure. I didn't know you could release a manual under GPL. Okay, so but what is this for? When to you write a custom device for QEMU. So I guess that's what this is for. I want to stay straightforward and just give an example of how to use QEMU to add a simple custom device. Let's say you are working with a prototype device and you need to start the development of your Linux device driver, blah, 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 but the board is not ready yet. You want to create a mock that will return predefined values. Okay, so this seems like this is maybe what the QObject model is for. It's maybe extending the functionality of QEMU. So Gemini is telling me about some possible applications of QMP, the ability to control the emulated machine from an API. So it says debugging and monitoring, debugging tools, blah, 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 performance bottlenecks, dynamic resource management. Cloud computing platforms often rely on dynamically scaling resources based on demand. QEMP allows your application to communicate with the underlying QEMU instance and adjust virtual machine memory, etc., add more cores, and so on. Automation and orchestration, integration with virtual machine management tools like KVM and libvirt. All right, and then security and forensics. And then I'll say who would use the QOM object. No. Is that what I wanted to know? I guess it is. So QEMU developers would use it, third-party library developers. Okay, so tell me how these features would be used in real applications by the Autobots or the Decepticons. Give 2 examples for each and really focus on realism and stay close to this transformer source material. I don't think it's going to comply. I think it's going to come up with a bunch of nonsense. Okay, so that's what the object stuff is for. We don't. So we've now seen. I opened this up and it was a lot of stuff. So we've now seen that it contains basically a programming language implementation. It's got its own type system. It's got an API that seems really flexible. You basically just send it strings, I think, and everything's kind of coded up in JSON. But it's relatively custom. It's not using like some existing like API embeddable thing. So that's so far it's pretty complicated. It all seems nice. It's all like really clear and well laid out. But that supports my thesis that there's too much here to really dig into all of this stuff. So I guess we're gonna maybe just do a whirlwind tour of like what all of the things are, and then if there's something that is both like close to the heart of what makes emulators, and also small enough to get some sort of grasp on, we can try digging in there. Here we're in ROMs. And we have things, these seem to be links out to other repos. So QEMU, Mac drivers, Sloth, IPXE, OpenBIOS, QBoot, CBIOS. So CBIOS is the only one that I know that I'm really familiar with, which is, I think, just like the BIOS that runs on, if you start up a QEMU machine, CBIOS is like the BIOS that you typically run into before you get to the bootloader. And we just have some like shell scripts for working with these various things. And let's just double check that this is a link out to some other repo. Yeah, well, no. I'm not sure. I'm going to guess that this is some, what's the word? Git commit. Can I search commits? Yeah, okay. It's some git commit from 2023. Okay, thank you. That was my theory. I just wasn't positive that was the case. All right, let's see what Gemini says. Repairing the arc, following the events, preparing the battle. Here's where QEMU chooses diagnostics. The arc's complex systems are beyond human or even basic Autobot engineering. Wheeljack, the Autobot inventor, could leverage QEMU to emulate the ARC's various alien subsystems by interfacing with the ARC's computer core through QMP. Wheeljack could diagnose malfunctions, identify failing components, or even test repairs virtually before applying them physically. All right, that's not bad. Remote engineering. Countering Decepticon technology. Okay, these are decent. I'm not going to read them all. Okay, so here's job.c. This is probably just some job. Long-running operations, background jobs. Okay. And we have a lot of different statuses. Undefined, creating, running, paused, ready, standby, waiting, pending, aborted, concluded, null. Okay, so there's different job stuff. Page, very common. Very meaning to like change as opposed to like really. This file must not be compiled with FLTO. Target page bits, target page. Set preferred target page bits common. The target page size is the lowest common denominator for all the CPUs in the system. I don't know if this means like literally. We take the CPU's page size and run the LCM algorithm on it. But maybe that's what they mean. So we can only make it smaller, never larger. And we can't make it smaller once we've committed to a particular size. I assume it just means it's maybe the minimum. Maybe here's the algorithm. Or no. This isn't checking anything on CPUs. Okay. At any rate, there's some page size stuff. I'm not sure what it means by very common. But something is bridge helpers. Known shortcomings. There is no manual page. The syntax of the ACL file is not documented anywhere. Parse ACL file doesn't report fopen failure properly. But what is it supposed to do? It's something that has ACL files and privileges, and I don't know if this is a bridge. I think this is maybe a bridge in the sense of a network bridge, because we have this iface here. Whatever if and amsys is. Let's look this up and see if this is networking related. Interface naming. Yeah, I think this is about network bridges. And I'm not going to look into it any further. Here's QEMU image, which might be interesting. I'm going to guess this is like the... I think the image is just the... It's not the... I'm not sure if it's the disk, but it should certainly be the like the operating system. We have, let's see, an image command struct, which has a name and just a function, which is some handler. And then we have a enum, which in a enum of options, such as pre-allocation, shrink, salvage, target is 0, add, enable, disable, etc. And we have some output formats, which include JSON or human. I'm guessing JSON's pretty human readable, but I'm guessing human has maybe no curly braces and like tabs and line breaks and stuff like that. Default cache is write back for data integrity. As data integrity is not important for QEMU image. Okay. I don't know why, but we can print some stuff. Some exiting behavior. We have a help. QEMU image command. So this is maybe the QEMU image disk utility as opposed to the image format. Okay. I was more interested in looking at the format, so I'm going to move along and see if I can find that elsewhere. So QEMU SASL has some note about if you want to use VNC remotely without TLS, then you must pick a mechanism which provides session encryption as well as authentication. What is SASL? Maybe it's a simple authentication and security layer, a framework for authentication and data security in internet protocols. Okay, so this is some authentication thing, and I guess it's really just a text file that has this suffix. I don't know if that suffix is meaningful by itself. Here's block dev. I was under the assumption that this was going to be a model of block devices in general, but let's see if that's true. We have IF max devs. I don't know what that means. IF interface, perhaps. You can override max devs. We have block interface type. So IF, I'm going to guess, is interface. So we have, it can be IDE or SCSI. Do people say SCSI? And we can do things like block dev mark auto delete. We automatically delete the drive when a device using it gets unplugged. Questionable feature, but we can't just drop it. Okay. So there's support for auto delete, which has a, pretty clean implementation. We have this global state code macro. I'm not sure what that does, but also job lock guard. So some sort of locking, I guess, of jobs, presumably because we're about to delete a device, and we maybe want to prevent other jobs from interfering. But once we pass this macro thing, or maybe it's a function as opposed to a macro. At any rate, it's a thing that's called, and then we call block job next locked on null to get a job. And while the job exists and it's canceled or deferred to main loop, and the block job doesn't have a BDRV, a block drive, I guess, then we're going to call block job next locked on the job and set that here. So if it's canceled or whatever, we get a new one, I guess. And if we have a job, this drops the job block temporarily and polls. So we need to restart processing the list from the start after this. So we call it job cancel locked on the job with false. And we do this while we have a job. And then we call dinfo. We set auto delete on dinfo to 1. I don't know what all that job stuff is doing, but it seems like it's where'd it go? It seems like maybe it was just block job next log. I don't think we're really doing anything with the jobs other than calling job has BDRV on BLK. So we're somehow checking which jobs have like a reference or are doing things with this device. I'm not sure whether we're canceling them or we're just ignoring them or waiting for them to stop, but we're doing something with those jobs. All right, and we have drive index to bus ID. So this is just some mapping. You give it a drive, I guess, and you get which bus it's on. And similar stuff. You have drive get. This seems about to be about manipulating the block devices rather than modeling a block device like as on a block by block level. Extract common block dev options. Okay, so I think that's what this is about. Maybe the here's block job. This is just some background job that has a device reference based on what we saw before. Here's block.c. And what is this going to be? We have B drive open inherit. Recurse has child. I guess this is going to check all the block devices recursively to see if one of them is the child. Is Windows drive prefix. Memory alignment path combine. If file name is absolute, just return its duplicate. Otherwise, build a path to it by considering it as relative to base path. All right. So this is more about dealing with block devices. I don't know how this is different from the previous one. Previous one was block job, but we have block dev versus block, and both seem to be somehow handling block devices. Okay, and then here's the system folder, which has things like memory, main. I think we looked at main, globals, DMA handlers, dirty limit, device tree, which is going to be some tree of devices, CPU timers, balloon, boot device, async teardown. And we saw main basically just called QEMU init. And I don't know if we chased down where that ended up, but maybe we'll pull out system and just check out other stuff as well. So target is what I thought it would be, which is we have ARM i386. It's the different systems. So let's take a look at, how about Spark? And for each of the systems, it looks like we have a CPU implementation maybe a machine as a model of the general QEMU machine. So we'll look at Spark's monitor, not monitor. No, we'll look at Spark's machine. We'll look at Spark's CPU header and its C file. And that'll be about it. So the header, we have a bunch of registers and a bunch of defines that are trap definitions. This is just some model of the CPU. What are these? I'm not sure. PSPEF, PSRMO. And we have SparkDevT, which has some stuff like the FPU version, the MMU version. Just, I guess, maybe like different configurations. Some cache stuff. Instruction cache freeze on interrupt. Data cache freeze on interrupt. Data cache flush pending. Okay. And then, so that's what's in the headers. The C file is presumably going to be implementations of some of the like parse features, add feature as prop, and presumably to add a feature as a property. And then what is the machine? The machine has a VM state description and a CPU timer. So the CPU timer has a version and a minimum version in some fields, including frequency, whether it's disabled, whatever NPT is, clock offset, and a Q timer. So these are just, with this information, you can model, I guess, the Spark system timer, or CPU timer. Then translation look-aside buffer entries. So you need to, I guess, populate the TLB, and you populate it with some tags, which is a Spark TLB entry, and a TTE, which is a Spark TLB entry. So I'm guessing this is basically key value pairs, key and value, and so on. So that is all probably pretty interesting, especially if you're interested in a specific piece of a specific CPU. But just in the interest of time, we're just gonna forge ahead. And if you want to look at any of that more closely, you can do that on your own time. All right, so here's hardware. This is presumably going to be similar. This is going to be models of different kinds of hardware, I would guess. So here's ACPI. Maybe let's look at audio and block. So block has, again, we have another block.c, but this should be lower level now. Like block p read non-zeros. Read the non-zeros part of block into buff. Reading all of the block is expensive if the zeros part of block is large enough. Therefore, check the block status and only write the non-zeros block. Okay. You can also read all the things, block conf, block size, etc. Hello from Korea. How goes it? And then we have some geometry stuff, block conf, geometry, and some block config type. I don't know what ptrans is. Presumably P is for pointer. Trans for translation, transform. I don't know. But at any rate, this is going to be like low level geometry stuff. Siles, maybe cylinders. So maybe, given that we have heads and cylinders, this seems to be imagining that we're reading from a spinning hard disk. Here's audio. I'm not sure if I recognize any of these. How about PC speak? This seems to be possibly simple. PC speak, PC speaker emulation. We have a state, which has ISA device. I don't know if if ISA is some abbreviation or if this is a device. I'm gonna guess it's some abbreviation. We have a memory region, a sample buff, maybe containing the sample to play, perhaps. A sound card, voice out a pit count, samples, play position, and so on. And then we generate samples given the speaker state. What was the sample buff? Let's see if we use the sample buff. So we have some sample rate times the pit count. And we take the pit frequency and do some shifting, divided by M, which is this thing that we got by multiplying the sample rate by the pit count. Cast that as a UN64 T. Or no, rather we cast maybe the pit frequency. Okay, and then we have multiple of wavelength for gapless looping. We set S samples to whatever QEM align down is, something about, I guess, aligning things downward in memory. The frequency times the length of the buffer and passing an M, and we divide by the pit frequency shifted and then do more shifting. I'm not sure really why, what all of this is doing sonically. And then we're gonna fill the sample buff, it looks like. So for all the samples, we set them to the sample buff. And if we don't have pit count, then we do something simpler. And then we have some stuff like callbacks, writing, initializing. Okay. So that's that speaker. Not really sure what this ACPI stuff is. ACPI interface. Let's look up ACPI again. Did we look it up before? I don't remember. Advanced Configuration and Power Interface is an open standard that operating systems can use to discover and configure computer hardware components to perform power management. For example, putting components to sleep, auto configuration, for example, plug and play, and status monitoring. It's from 1996. Okay, so this is going to be pretty huge. This can do a lot, so maybe we're not going to really look at it. But we have CPU hot plug, RD. Maybe you can hot plug a CPU. And presumably you can hot plug a disk. What else can we? PCI bridge, trace events, memory hot plug. I guess maybe you can hot plug RAM and similar stuff. Can you really hot plug a CPU? Modern advances in system architectures have introduced advanced error reporting and correction capabilities in processors. There are a couple OEMs that support NUMA hardware, which are hot pluggable as well, where physical node insertion and removal require support for CPU hot plug. Okay. Such advances require CPUs available to a kernel to be removed either for provisioning reasons or for RAS purposes to keep the offending CPU off system execution path. I don't think I've ever seen what a NUMA system looks like. Photo. How about we try hot pluggable CPU? Let's try adding data center. All right, well, no. This is some disk. And maybe it's just like you have like a whole unit. I don't know if you have like a whole unit like this that you pop in, or you have like I don't know if they're like inserting it into the motherboard. That can't possibly be what they're doing, but somehow you can hot plug CPUs, and ACPI supports that. And I support ACPI. All right, so that's hardware. And I think that, let's see, I/O, we're basically just going to ignore now. We have a DNS resolver and like socket support, TLS, utilities. Should we look at WebSocket just for fun? First of all, this is not syntax highlighting. There we go. Okay, so this is WebSocket support. We have lots of these all caps defines. WebSocket protocol binary. Upgrade. So these are just defining these strings as like types, and so on and so forth. And we have like handshake, send, res. And I guess they have to implement all this stuff. Do they have to implement a whole TLS thing? Where did TLS go? Channel TLS. So we have this write handler, read handler, new server, new client. What about handshake? There's handshake IO, handshake task. I'm hoping that this ultimately delegates to whatever. Yeah, it has to. Trace QIO. I'm not sure really why it needs TLS channel support in the first place. Like, why isn't that the operating system doing that? Maybe it's for the QEMU application itself to communicate to like to APIs or whatever. Almost all network services in QEMU have the ability to use TLS for data encryption. At a high level, QEMU requires certificates, blah, 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 blah. The GNU TLS package includes a command called certtool. Okay. You can set up certificate authority, issuing client certificates. Yeah, so I'm guessing that this is for just communicating between like QEMU client and a QEMU server, like maybe using an emulated VM from a different machine, as opposed to like, I don't know if this is in the path of any network call you make in the emulated OS, but let's ask, why does QEMU need TLS support? Secure live migration. During live migration of virtual machines, QEMU with TLS encrypts the guest memory and device state being transferred, etc., etc. Authentication. From row client. Yeah, okay. So that's consistent with my theory. So let's move along. FPU self-float parts.inc. I don't know what these .inc files are. The code in the source file is derived from release 2A of soft-float floating point arithmetic package. Those parts of the code and some later contributions are provided under that license. So maybe .inc for include. Parts N, add normal, floats part N A, floats part N B. Expdif is the difference between the exponents. If the difference is bigger than 0, we call fracture with B in the expdif, etc. Okay, so this is just some floating point implementation. Nobody wants to build a floating point implementation from scratch, so they're including somebody else's implementation. This was made possible by the International Computer Science Institute in Berkeley, California. Fast emulation of guest FP instructions is challenging for two reasons. First, FP instruction semantics are similar but not identical. Are similar to what? Particularly when handling NANDs. Second, emulating at reasonable speed the guest FP exception flags is not trivial. Reading the host flags registers with a FE clear accept and FE test accept pair is slow, slightly slower than soft FP, and trapping on every FP exception is not fast nor pleasant to work with. Okay, so there's technical difficulty emulating floating point. Here's backends, which I think we already looked at. This is character devices, which we are not going to look at. That leaves us with system. I think I have to get going, so I don't have any more time to look at system, but that was kind of as I intended, because I think we've already looked at the main parts of system that we wanted to, and maybe the only thing I'm curious about is ballooning, Generic balloon handlers and management. I don't know what a balloon is. Have balloon. Let's look up KVM balloon. I don't know what is ballooning here. Dynamic memory management. Okay. So I think it's memory that's ballooning. So that is QEMU. It's a huge project. There's a lot going on, and it's also really technical. So we just really did a whirlwind tour to see what the various folders were up to, and also try to get enough of a handle on how it works to get a sense of what it, if you were interested, for example, in contributing to QEMU, I think you'll have a little bit better of a time digging into which like subcomponent is interesting to you. And there's enough there where both here and some of the other projects we've looked at, you get kind of these like implementations of little programming languages. So QEMU has the QObject model, and it's like own type system. And all of that can be a good starting place if you're interested in some of the basics of programming languages, but don't want to look at something like fully featured, maybe like Python or JavaScript that has had decades and decades of like corner cases and optimizations and stuff added to them. So that's all for today. I'll be back tomorrow at 10 a.m. Eastern for doing more code reading. Thanks for watching.